sure it's working.
Live streaming is on.
Okay.
And the stream health is good and green. That's good.
Yep. Yeah, I didn't have time to change it. Normally, I have the slide selections on a different screen. Can't do that with Jitsu. Out of curiosity, what is 13156777831?
A long number?
That's my phone number.
Oh, okay. Did the Linux Penguin ever get a name?
Tux.
That's right. Yeah, that's right. Welcome, Arnold.
Thank you.
By any chance, do any of you run Raspbian mail servers with SSL? Apparently not.
Is on.
I'm running Raspbian with Kubernetes.
What is Kubernetes? I'm not familiar with that one.
It's a way to run containers in a highly available manner.
Okay. Yeah, I'm looking to run a mail server. I currently have Postfix installed with Dovecot and TLS Manager and a couple other things. And my certificate is valid, but and I thought I had it working more than a year ago. But for some reason, in the last couple months, it hasn't been transferring with TLS. I open up the port, but it doesn't accept the connection if I open it up with Telnet or with OpenSSL, OpenSSH. And so the mail's getting through without encryption, but unfortunately it's not getting through with encryption.
Oh. Are you using the certbot from the Let's Encrypt people?
I am using certbot, that's correct. Actually, this is the first time I was using that. Before I was using GetSSL, I think it was, which was a different Acme client. I did the original certbot. I didn't like its insistence on running as local root. So I used get SSL, which I could direct it where to put its stuff, and didn't need to give it root permission at all.
Right.
I'm not sure how recently they updated CertBot so that you can so it's not as intrusive.
Yeah. Okay.
But no, I'm pretty sure that I've got an MX record. The only thing I don't have, which as far as I know shouldn't actually be necessary, is my ISP doesn't supply a reverse DNS.
Yeah.
My understanding is the MX record should be sufficient.
Okay.
So,
That's the record for the mail server, right?
correct. The DNS is translates the host names into IP addresses. Then, as a in order to somewhat authenticate mail servers, they started adding. They added an MX record, which is a record stored on the DNS that identifies a mail server for the particular host. So if you own the domain, you also presumably are the only one who can change the MX record, and therefore it's a valid mail server.
Right. Are you running a mail server?
Yes.
Oh,
And
okay.
that's the whole point. Yes. The problem is that it's not working with TLS at the moment. It's only, and I'm pretty sure last year it was working with TLS, so I don't know what changed. What broke or what changed.
So you're running naked through the internet.
Yeah. And I'm trying to avoid that. Which is why right now I'm not giving out my email address in general.
So the protocol you're using is SMTPS?
Correct. That's what I'm trying to use. But it's not running. In other words, when I connect to it, let's see, I'm trying to remember. I think I can connect to it locally over OpenSSH, but when I try connecting to it with a mail client, it doesn't negotiate the TLS for some reason. It either uses straight SMTP, or it hangs waiting for the handshake, the TLS handshake to take place.
I might suspect a firewall.
I thought that too, but I seem to be going through the correct. I seem to have the correct ports open. I forget what they are. 587, 4970, or something like that. I forget the number. What the ports are. But that's, I guess, really is somebody who might know something I'm missing. So if Shay or anybody you got there knows, well, I'd be interested in talking to them later.
Let's see. Secure TLS is 587.
That sounds right now that you say it.
Yeah.
the other question is, has anybody there unlocked an Android cell phone or loaded Lineage OS, the replacement for Cyanogen?
Tim Fowler would be my guess.
Okay.
I can give you the Nexus is the 5 and the 6. That would probably be the best two to run Lineage.
Okay, the Nexus, and what are those? Are those brands of phones? Are they distros? What are they?
No, you wanted to run Lineage on a phone?
Yes. In other words, I have an Android. Currently, I've got two of them that are Motorola Razr M and Droid, the original Droid, which is actually what I'm looking to replace.
Oh, if you try to run Lineage on it, yeah, you have to see if it's supported by them. Some of the ones, they've dropped some support for some of the phones recently.
Okay. I'm not. So is the Nexus then a brand of phone?
Yeah.
All right. Well, I definitely would like to talk to you. May I get your contact information?
I've only ran it on one phone, and it's one of the ones they just dropped the support for. So
okay. Well, I'm
kind of looking for a new phone myself.
Okay. Well, then the two of us maybe can get together, and I might point out one of my basic. At this point, I'm at the stage where I have seen a huge amount of information on the internet regarding what do they call it? Not loading. There's another name, but adding an OS to a Android. But unfortunately, I found out most of it is frankly obsolete or inapplicable. And so I really need somebody who's at least had the experience of what works that can separate, or at least would have a better probability than I of separating the noise from the obvious noise from the useful stuff. So, if you don't want to give me your credentials over this thing, maybe if you'd be willing to give them later to.
Yeah, you can post either in the mail forum, or I can give you my email address. It's just kind of long.
Well, that's okay. I don't mind a long email address. Mine would be too. If you feel more comfortable though, you can give it to Ben. I can get it from Ben.
Okay.
You can just type it in the chat there.
That'll work.
Oh yeah.
I'm okay with that.
All right, it's in the chat.
Got it. I hope. And yeah, I'll try and contact you tonight or in the next few days. Yeah, since my mail server, as I said, is not yet working quite right. I've been doing most of my stuff with chat, i.e. SMS.
Hey Matt, do you want me to edit that out when I'm doing the video?
Yes, yeah, that'd be great.
Okay.
Yeah, that's what I was referring to when I asked if you might be more comfortable giving it to Ben. I can get it from him. How many people usually show up at the last minute?
How many? Well, this is about normal. So we might get a couple more.
Okay. Well, I will take advantage of just a minute or two. I'll be right back.
Okay. How you doing, Jace? Staying busy? Okay. All right. Good. Does anybody want to be Don Pardo, the old Saturday Night Live announcer?
Do we remember him?
Some of us.
Apparently, we don't.
I know who he is. I have a
I-
bunch of the old. I have a bunch of the old Saturday Night Live seasons on DVD.
I actually even met him in New Jersey one time for at a college bowl.
Yeah, Jimmy Fallon said he talks in real life just like he talked on the TV.
Yes. Yeah,
So
I
you
remember
can confirm
that.
that, Robert?
I'm sorry?
You can confirm that?
I can confirm that. Yes, I can.
That's funny. Okay, well, it's 6:30, and we got a special treat tonight. We have got Dr. Robert Meier, that is going to present the Apollo space program, and I'll let you give the title and everything, Robert. So why don't you go ahead and take it away?
Will do. All right. As pointed out, I'm Dr. Robert Meier, known as Bobby here in North Carolina, Bob in northern parts of the U.S. And let's see, a few minor questions to begin with. How many people here were alive when Apollo 11 went to the moon? Okay, didn't. So apparently, I'm the only one. How many people here think that Apollo 11 was a hoax and we didn't go to the moon? I'm glad to hear that. Or not hear. Good. Okay. How many people here know somebody who thinks that Apollo 11 was a hoax and we didn't go to the moon? That's amazing. Okay. Nobody here knows apparently any people educated in the Indian school system. That's the Indian subcontinent, by the way. All right. Well, okay, now some other slight questions. How many people here are confident they could travel out of state to a destination they hadn't been to before without GPS and without getting lost? No one. Okay. Well,
Do we
Apollo
get a
11. Go ahead. What?
Do we get a paper map?
Yes, you can use a paper map.
Then I'm confident I could get somewhere without getting lost.
Very good.
I'm pretty sure I could too.
Very good. I've actually given this at other venues, and most of the people who weren't alive when Apollo flew would answer they would not. They always use a GPS. They wouldn't know how to navigate without it. But before Apollo, GPS didn't exist, so they had to travel roughly 500,000 miles, 500,000 miles, without it. And in fact, the fact that we use GPS today is good proof. When you get a skeptic, somebody who says it didn't take place, GPS is actually proof that they can observe themselves that we went to the moon. And that'll be part of this talk. Apollo was the goal of Apollo. Oops. There we go. I'll tell you when I'm changing screens or changing slides, and if somebody doesn't see the slide in a few seconds, just let me know. So I just changed slides to the goal. All right. The goal was landing a man on the moon and returning him safely to the Earth. Everybody here know where that came from? Anybody here not heard that phrase before? Okay. That was President John F. Kennedy in his 1961 speech, just after he'd taken office, just a few months into it. And the other part on this is, and return him is before the decade is out. Now, at the time, going to the moon was often used as the cliche phrase for something impossible. How many people ever heard, "To the moon, Alice, to the moon"? Can anybody tell me where that's from?
Honeymooners.
I'm sorry? What do you say again?
Honeymooners.
Honeymooners, that's right. Jackie Gleason to Audrey Meadows. When he was frustrated, he was going to belt her to the moon. That was, at the time, as I said, a phrase for something impossible. In fact, how many people here ever saw an engineering textbook, college-level textbook, from about 1977 or before? Up until 1970, go ahead. Up until 1977, the most common physics textbooks, I said engineering, physics textbooks for engineers, was university physics. And it had a chapter in it that was to teach how you could prove something couldn't be done, and therefore you shouldn't waste engineering time on it. How to use physics to prove what wasn't available, and thus eliminate wasted effort. That chapter looked at all the ways proposed to go to the moon and proved they were all impossible. We'll get to some of those in a minute. Okay. In general, the problem required solving problems at scales of distance, speed, and weight that never or seldom were encountered before. Many were never even imagined. The experiments they did, they tried familiar technologies, they tried unfamiliar technologies, ideas from everywhere. From fiction, science fiction, from students, from engineers. Almost anything and everything was tried. And the results? Most failed. Most of the ideas were ridiculous for the very simple reason they didn't work. But some did work. The best ones got us to the moon, and a lot more that worked never saw use in Apollo, but produced a lot of new profitable industries and made older industries more profitable. And right now, anybody name something they've got right now in their pocket or in the room they're using that wouldn't be around if it hadn't been for Apollo? Anybody want to say something?
Cell phone?
Cell phone, that's a good one, right? The microelectronics in that would probably still not be around. And a lot of the switching that they depend on, that the cell phone network depends on, also would not be around. Certainly not as something spread over the planet. Okay, anything else? Okay, well, one we mentioned was GPS. Who's got does anybody have GPS on their phone?
Yes.
Okay, yes. Does anybody not have GPS on their phone? Okay, that's what I figured. That's one that simply would not be around. It was and we'll get into why. Okay, but a lot of other things, like we wouldn't have the lasers that we commonly do, the cameras that are in those same cell phones would certainly be much more expensive if the collimation technology hadn't been amortized by the Moon Project. Okay. And so this series will explore those. In particular, I'll concentrate on GPS, Velcro, cruise control, and system engineering. We probably won't have time for all four of them, and there's also laser that's an option. So after we go through one or two of these, you can pick which one you want based on time, which one you'd like to look into. All right. So the goal of touching the moon. It basically is described here. It's like tossing water balloons to the top of a skyscraper. What's the tallest building in Columbia or in Greenville or wherever any of you are right now? What's the tallest building? Shay, where are you and what's the tallest building there?
I think it's the Itology.
Itology?
Yeah.
Okay. And how tall is the Itology building?
It's about 18 floors, I think.
18 floors. About. So you don't actually know better than probably about 10%, am I right?
Right.
Okay. So if 10% over 18 floors, you're probably talking about a 40-foot air. And do you think if you tossed a water balloon and you were off by 40 feet, do you think the balloon would survive?
No.
Probably not. And especially if there's any wind, there's other factors in between, in other words, that would affect it as well. Okay. So lots of ways that have been proposed to do it. And these ones I'm mentioning are all ones that were in university physics. If you can get hold of, actually, it was later than 77. I think it was actually up through the late 80s, early 90s before university physics finally removed that chapter. Although obviously after the 60s, it was a bit more of a bit of a point of entertainment. Still instructive, though. Okay, Jules Verne proposed a cannon. Problem with a cannon is you launch at escape velocity. Well, what happens to meteors or other things that encounter Earth's atmosphere at escape velocity? They burn up. So if you start off at escape velocity, you aren't going to get very far. How many of you, one of you say, Jason, what would you guess is the temperature at which a rocket jet comes out of a rocket? Can you make a guess, Jason? Anybody else?
900 degrees?
You said 100 degrees?
900.
900. Okay, actually you'd be a lot closer to 100. An ideal jet from a rocket would actually have its exhaust temperature at the same temperature as the reactants, which in the case of the Saturn V were at well below freezing, well below 0 degrees Fahrenheit. In fact, they were low enough that the temperature would probably not burn your hand. How many people here have been by an airport and seen the blast deflector where the runway gets close to a road? I believe the airport at Grenville has such a blast deflector. Is any of you near Grenville or been there? Okay, apparently not. Now, has anybody noticed those deflectors are usually made out of wood or plastic? Would you want to put a blast deflector made out of wood or plastic behind the exhaust of your car?
No, not really.
Right, it would burn up. The Saturn V launch, if all of you saw it, and has that bright flame, not because the jet was that hot, but because it encountered sea level air pressure. You were putting some, I think it was 500 pounds a second of reactant mass at escape speed at sea level pressure. And so, like a meteor, it grew incandescent, and that's what creates the flame. You don't, that same thing would happen to anything launched by a cannon from the surface of the Earth. Okay, anybody here unfamiliar with Buck Rogers, Doc Smith, or Robert Heinlein? Anybody want to say what they're noted for?
Space opera.
Space opera, right. Doc Smith wrote the Gray Lensman, which is the series that actually gave that started the name space opera. And Buck Rogers was another very good one. Robert Heinlein is excellent. In his things, Space Cadet, The Moon is a Harsh Mistress. Highly recommend them. Actually, I'll recommend all of these. In the case of Buck Rogers, see the one from the 1930s. The one from the 1980s I wouldn't recommend. If you disagree, ignore my comment. But anyway, they tended to treat rockets like seaborne ships, with the jets continuously fired and throttled to shape orbit, to continuously adjust the course of the spacecraft similar to a ship at sea. Now, and they tended to both take off and land straight up and down, what's called direct in and out. The only problem with that is it takes exponential fuel. To land straight down, you have to use enough fuel to slow down and hold yourself slowed down as you go through atmosphere. Now, the moon, when they were designing the lunar mission, the engineers believed the moon had no atmosphere. This is despite the fact that the astronomers had been pointing out sight of meteors, glowing meteors in the moon's impacting the moon. So they actually sent a model to the moon, which was called Ranger, and its principal purpose was to get the exact distance to the moon. Well, it happened that it used an accelerometer during boost phase to precisely control its velocity at Earth departure. That accelerometer, though, was still feeding signals as it approached the moon. And the anecdote goes that they were surprised when it showed a deceleration prior to impact with the moon. It had encountered the lunar atmosphere. Too thin to, if you're trying to breathe it. In fact, at the time of Apollo, the thickness of the lunar atmosphere was less dense than the hardest vacuum that up till that time had been produced on Earth. But it was still hard enough that the lunar excursion module's legs would have been blown off had it tried to do a direct in, direct out landing. Okay, now they did actually end up doing the Didos with the Surveyors and the Luna, Luna being one of the Soviet lunar missions sequences, but they carried very little payload, and obviously both we and the Soviets shifted off that approach. Okay, so how do you guide yourself to the moon? Well, how do you know when, if you are, for instance, driving a car, how do you know when to stop when you're getting too close to something? We use stereoscopic vision for things that are close, and we use landmarks, signs, striping on the pavement, etc., in order to tell distance from things further away. Well, if nobody put any signs on the moon, how do you know how far away it is? The best that we didn't have something accurate enough, more accurate than actually, not much more accurate than for the Itology building, knowing its height within maybe about 10 feet. We didn't know any better how close or far the moon was, and the moon keeps changing. It's as it moves around the Earth, it gets significantly closer and further away. So we had, and remote control from the ground, time delay was 1.5 seconds. So there was no way to adjust it from the Earth, to guide it in remotely, like you could guide a remote controlled aircraft. But what could we use? Doppler. Anybody here not know what Doppler is? Anybody want to give a 10-word explanation? All right. Well, Doppler is that frequency changes with speed. If you're in an airplane and you fly away from an AM radio station, you actually have to tune the frequency down in order to keep receiving the station. Now, in the AM frequency band, commercial frequency band, it's not so significant, but they actually had to invent FM for World War II military planes, because as they were using higher frequencies up in the tens of megahertz, and at that frequency range, and certainly up into the UHF television and later higher frequencies, the frequency change would be enough that you couldn't even listen to an AM station. It would become unintelligible. All right. Well, speed also changes in gravity. Amateur radio operators have known this for decades. It was anecdotally explained by Einstein, and so to this day is called the Einstein effect. As radio signals sent from a transmitter on a hill are received at a higher frequency down in a valley. Now, this was the reason why crystal TV sets didn't work without the addition of what's called automatic frequency control, or fine-tuning, mechanical fine-tuning, before. Well, that can be used, though, if you know with precision the frequency of the transmitter. So Ranger carried a precisely calibrated transmitter, and as it traveled to the moon, it allowed us to refine Earth's gravitational potential, and by a factor of about 100, to where, which is one of those things you need in order to know how to get to the moon. You have to have that Earth gravitational potential. You also need that to a minimum of about 12 places accuracy for GPS to work. So that's the next one we'll get into. Any questions so far? Okay. Let's see, so that was, which one am I on here? Proposal. Guidance. And planetfall. All right. Now, the way they handled the problem was twofold. One, we used Surveyor to get a more accurate measure of Earth's gravitational potential, sufficient to land Surveyor, and it's at least sufficient basically to get close enough to the moon to use to shape course toward landing, what's called planetfall. Just as an airplane approaching from en route transition to what's called approach, basically closing on the airport and lining up with it before going into the pattern, before going into the actual landing sequence. So to approaching a planet, you go to planetfall, where you transition from en route travel, where you don't have to make many corrections, to where you're gradually trying to get yourself in a position to do that precision landing, the Dido approach, that direct in, direct out. The problem with coming in at what is called a lo-fi orbit, i.e. nearly parallel, is that a very tiny change in your speed causes you to fall faster, dramatically so, towards the surface. And too slow, you likewise skip by it. So precision is needed. And it's so they also needed to know the moon's gravitational potential. And this was, anybody ever asked themselves why Apollo 10 didn't land on the moon, why they waited for Apollo 11? Does anybody remember what Apollo 10 was, Snoopy and Charlie Brown? Anybody not know what those were?
Wasn't that the docking?
Wasn't that the what? Say again?
Is that the docking or the testing the control of the lens?
Well, that actually was Apollo 9, was where they did most of the docking testing, the flight testing. Apollo 10, they actually circled the moon, and they not only did the docking and undocking, that not only did the docking, but they undocked and actually went into planetfall. They actually disconnected from the command module, fired the retros, and went down into an orbit. The only thing they didn't do was fire the engines enough to actually make the landing. In fact, they deliberately loaded the descent stage with water instead of fuel, just to prevent the astronauts being tempted to try and make the landing. Because at the time, the error in the moon's gravitational potential was only gave them an estimated 1 in 4 chance of it even being possible to make the landing. There was 3 out of 4 chances that even if they had perfectly used every gram of fuel that the LEM was capable of, they still would have either crashed into the moon or run out of fuel too high up. But the Apollo 10 flight was the last calibration. It measured the gravitational potential with sufficient accuracy. Now, gravitational potential is not something you can measure close up. It's a natural hash. On the Earth, anybody here ever tune a grandfather clock, a pendulum clock? Okay. A pendulum clock is really a gravitational field strength meter. If you move it just between floors, it's enough to cause the pendulum clock to now run fast or slow by seconds per week. Put it over a garage, and whether you drive a car under it or not is sufficient. The field strength of the Earth varies over it, what are called mass cons, by substantial margins. Enough that there is no possibility of measuring the gravitational potential of the Earth at less than several dozen Earth diameters away from Earth or any other astronomical body. So the ability to measure the gravitational potential was proof that we had, this is one of the proofs you can tell people about, was proof that we had complex equipment, precise equipment, at several dozen diameters away from Earth. And at the time, without computers, there was no way to automate that equipment. It'd still be very expensive to do that today, and impractically so. But we had humans that could operate that equipment and make the precise measurements. So that's not actually proof that they landed, but it's proof that they had the capability to do the landing. Okay. One of the things that somebody who was alive at the time would probably remember is after the Apollo 11 landing, the State Department published this number, the gravitational potential of the Earth, to 12 places. Now, not everybody still alive probably knew at the time what the significance of that was, but it was a hash that could be checked. Just like with current encryption techniques, you can generate a hash, a digest, and prove that a file hasn't been tampered with. Likewise, this hash could be verified and proven to be the correct one for the Earth, even though it couldn't have been measured or calculated in advance. And I might add, by the way, they subsequently used the gravitational potential to 14 places for the current GPS system. It has changed, by the way, in that 14th decimal place since the GPS system started in the 70s. And if they didn't correspondingly change that in the information distributed by the satellites to the GPS receivers, your GPS would be off by, at this point, well over 100 meters. Well over 15 meters. Probably closer to 100. You have to do the calculation. And within a century, it would definitely be off by hundreds of meters. Because the Earth is still accreting, if you're not already aware of that. Okay, so... okay. And there we go. That was what Snoopy. It had the AGC, the autopilot, which we'll talk about next, and that reduced the error to that 0.01%. So that's one of that GPS system is one of the benefits of Apollo 11. Consider how big an impact that has had on worldwide industry and U.S. industry. Okay, any questions before going on to the next output, cruise control? Any questions? No? Okay. So what was cruise control? Well, the goal was to make a soft landing, one the astronauts could walk away from. And that means you start out at escape speed. You have to decelerate from that. Now, escape speed on the moon is about 2 kilometers a second. And you're starting at a high altitude, a minimum, in fact, of about 400 meters, because that's where you would make atmospheric interface with the moon and start worrying about aerodynamic damage to your spacecraft, and like having your legs blown off. So you have to get down to walking speed and do it using less fuel than you brought. The longer it takes you to do it, the more fuel it's going to take you, the heavier you're going to be, which is going to take even more fuel. Very quickly becomes an exponentially accelerating problem. Okay. Now, the proposal for doing the soft landing was DIDO, direct in, direct out. Standard method that had been used in science fiction for decades. I think for more than a century, actually, at that time. And before Kennedy's proposal, that was actually what NASA had been studying, what they called NOVA. Anybody hear of NOVA before, by the way? Okay.
Yeah.
Oh, good. Who's that? Who's that who heard of it?
Andy?
Indy. Okay. What can you tell us about NOVA?
It was a really big rocket that was infeasible.
A really big rocket. Exactly. And, however, it turns out it would have had to be far, far bigger still, because direct in, direct out would have required that they slow down enough before getting to the touchdown so they didn't suffer damage. It turns out it would have required 64 Saturn V's to launch the original NOVA approach. Now, I referred to you before to phi. Phi is the angle between the horizon when you start slowing down and the horizon. So if you come in DIDO, you're coming in straight down. And if you're coming in straight down, all you need is a governor. Simply calculate your distance from the surface with radar and slow yourself down proportionally. Now, the ideal is that you would actually free fall, until the last possible minute, and then you'd fire your jets at full throttle. And that would require the minimum fuel to touch down. Now, your jets had better be, able to handle that, and if you miss your timing, you're going to end up landing below the surface. Not a good idea. Or above it, but it's a simple problem, and easily automated with a governor that could have been built anytime radar was available. But do that on the moon at 2 kilometers a second, and the aerodynamic load is about equivalent to a Cat 2 hurricane. The LEM, made basically out of aluminum foil in order to keep it light enough to launch through Earth's atmosphere, would not have survived, would not have been undamaged enough for a successful landing. Surveyor was the scale model of the NOVA proposal. And Surveyor, after they found out from the Ranger that the Surveyor's Dido wouldn't have worked, and the prior Lunas by the Soviet Union that crashed, presumably crashed because they hit the atmosphere that was unknown and thus failed. The Surveyor landed, but it landed by them having to make last-minute changes. There wasn't time to totally redesign the thing, but they did load extra fuel, taking away cargo, payload, and they changed the programming so that it actually started slowing 5 miles early. It slowed from that 2 kilometers a second at 4 Gs down until it was slow enough that they would actually do the Dido straight-in landing. Okay. Well, if you come in from the horizon and slow down above atmosphere, then it's all you need. Then the aerodynamic load is nothing but a light breeze. I take it everybody here has noticed that when rockets launch, they launch straight up, but very quickly they turn horizontal and fly toward the horizon. They do that to get through the thickest part of the atmosphere with the booster while they're still slow enough to not use excessive fuel. And then once they get up into thinner atmosphere, then they go for speed. And it's speed that sets the boundary to space, not altitude. The altitude, official altitude for space is only 100 kilometers, about 62 miles. But the speed for space is about 7 kilometers a second or more. And think a minute, which one is harder to get? 62 miles or 7 kilometers a second? That's, by the way, about Mach 25. So imagine trying to drive your car, how long it would take you to get your car up to Mach 25. Now, at low 5, as I said before, if you're not precise, gravity bends course down. All right, how many, okay, if you know any pilots, you can ask them. Light aircraft generally do not have brakes in the sense that a car does. They coast to a stop once they land, or they use aerodynamic braking. The jumbo jets were the first ones that they made the what are called vernier brakes for, where it's essentially a fly-by-wire system. Pilot commands deceleration, and a servo system applies the necessary braking or releases it to accomplish that. The reason was because in the early days of flying, when they tried putting brakes on aircraft, normal automobile-style brakes, the problem was that as the plane slowed down, its weight increased. As its weight increased, its braking effect increased. And so tapping on the brakes after touchdown would be a self-accelerating process, and too many planes nosed over. The brakes grabbed, bit in unexpectedly, and the plane would go over on its nose. So today, brakes on a plane are usually on-off. There's a cam that, and they really just slow you down. They're toe brakes, and you use them to turn, but they don't actually stop you very well. All right, you have a similar problem. You can think of landing on the moon as like trying to do a short field landing. Come over the trees, touch down, and come to a stop in the shortest distance, which takes a little bit of skill to keep the aerodynamic drag up so you slow down rapidly, like use your wings like a parachute. and then bring the nose down, while you still have enough control to deposit it gently on the runway. Well, similar problem. As they would slow down, gravity would bend the course down, magnet, which would cause them to speed up. So you needed precision in your approach. During the Apollo returns, the news media used the example of laying a piece of paper over a basketball and claiming that the thickness of the paper was the precision with which they had to make atmospheric interface at Earth. If they were above it, they would go skipping off like a rock skipped over a lake. They wouldn't grab enough atmosphere. If they went too deep, they'd burn up before they could slow down enough. Well, similar situation even occurred on the moon, not due to atmosphere, but just due to the fact that the planets form and the moon forms because things that are going at escape speed generally don't fall into the moon. They tend to fly around it. So if you're coming in at escape speed, you need to be very careful to bend your course just right. Now, and it's a very nonlinear curve, so you need to anticipate and correct early. Oops. Okay, proposal. So they created the LEM AGC to do this. Okay, excuse me again. All right. They needed a way to. They created a fifth-order polynomial, which actually simulated takeoff at a constant thrust and pitch rate, and then from this they could calculate what the ground speed and altitude would be. And then the ground speed and the altitude were the figures that they got from the radar. As the astronauts made planetfall to the moon, they were lying on their backs looking out away from the moon, and the radar was beneath their backs, or behind their backs, depending on your point of view, pointing down at the moon and giving them their velocity over the surface of the moon and their altitude, using, by the way, the same technology that's used for the jumbo jet auto-land system, also for the Norton bomb sight from World War II, if any of you have heard of the Norton bomb sight. Major secret during World War II. It's now in the nose of pretty much every jumbo jet, and it was what the radar that they used for aboard the LEM. Okay. Now, from calculating the expected speed and altitude, velocity and altitude, they were presented with a gyro. They called it the 8-ball. You probably heard that phrase if you saw the movie Apollo 13. And it told them what their attitude was, where they were pointed. They had two screens, two little CRTs, that presented a dot on crosshairs, which were the prediction of what the horizontal velocity would be and their downrange and altitude when they got to the high gate. That was the point above the atmosphere where they would begin the vertical descent, or almost vertical descent. From that alone, humans, just keeping the dot centered on the crosshairs, could make the landing. Though at the time, no computer system could. No analog computer, no mechanical computer. And it was even 10 years later, when the Vikings went to Mars, they had the first automated systems that successfully made a low-fi orbit, and they only gave them each a 50-50 chance. Now, they came up with this approach based on a lot of ergonomics. So let's see. We get out of it today the cruise control. At the time, they called this man in the loop. And NASA did the human factor study on this. One of the things where they did tens of thousands of tests, and we benefited from it since. There had been some successful man-in-the-loop control systems before, but there was no engineering to it. It was more trial and error, and they tended, as a consequence, to be unusual, and expensive, and unreliable. So, in 1913, you had a wing leveler, one of the first things devised, worked similar to a sea anchor. Piper, in 1958, applied what's called Kalman filter theory, which then was not well known. One of those esoteric math theorems that most people at the time would, if they heard of it, they'd say nobody'd ever use that. Well, Piper used it for their autopilot, and that autopilot being their brand name, the FAA adopted that word and paid Piper for it, and it became the official term for the hold and command logic in aircraft. The Apollo AGC was the first time that it was engineered, and as a side benefit, they introduced Kalman filters to engineers, now used in everything from oil tankers to robots to plant control, but at the time, not well known. One of the amortizations that NASA gave us benefits from, that the Apollo program gave benefits that we reaped outside the moon project. And it was adopted quickly. 1965, the AMC cruise control was the first one mathematically designed for public use. They found out, by the way, when they used that man-in-the-loop approach for the LEM, you didn't need a skilled pilot. In fact, they found out that after about 10 tries, most people just off the street would be able to land the LEM. Humans are very good at eye-hand coordination, the eyes giving the state, and the brain predicting what's going to happen if the state remains, and the hand making the changes to the state, which is now how the cruise control on your car works. The state is reported by the speedometer, and you set or tweak, bump up, bump down, depending on your particular cruise control, to adjust that state to be what you want it to be. Or either, okay. Well, that's sort of the end of the cruise control. By the way, had anybody before heard the phrase man in the loop? Okay. Cruise control was again a brand name, I believe AMC created. It might have been somebody later. But when it was first divided, when it was used for NASA, they called it man in the loop because the marketers hadn't got around to calling it cruise control yet. Okay, so we've covered two, and what's our time look like? It's 19:21. It's been an hour. So we can go do a couple of different things. Velcro, system engineering, or laser, which all came out of NASA. Not necessarily invented, but and microelectronics, excuse me. So anybody want to select one of those four for, I assume we have time for a third one, or how much time do we have, Ben?
we've got until 8 o'clock. But if you want to go long, I'm sure people would hang on.
Okay. Well, anybody want to pick Velcro, systems engineering, laser, or microelectronics?
System engineering.
System engineering. Okay. Anybody object? All right. The one who said they were interested in system engineering, you want to give a, say, 10-word description of what system engineering is?
I'll leave it up to you.
All right. Okay. The goal. T-minus 100 months and counting. Kennedy's deadline was before the end of this decade. And depending on who you talk to, like today, the end of the decade could either be December 31st, 1969, or December 31st, 1970. If you talk to a historian, they'll call it December 31st, 1970. If you talk to most Americans at the time, they would have said December 31st, 1969, which is what the T-minus 100 months is, a little over 8 years. Now, less than 8 years to do the impossible. NASA's original NOVA approach was, as we said before, the Dido, launch from Earth, similar to science fiction like Robert Heinlein's Space Cadet. Highly recommended book, by the way. Launch from Earth, that had a strong steel hull, which they wouldn't have used because it would have been too heavy. NOVA probably wasn't going to depend on nuclear jets. I don't think they had decided on the engine. And but at the time, they were starting to learn the consequences of, or the side costs of nuclear energy. I don't know if they were still doping coins. I don't know if anybody remembers. They actually used to make currency radioactive as an anti-forgery technique. Anybody have any coins from that period that they know are from the 1950s and 60s? If you have, you might want to check them and find out if they're radioactive. But later on, they were in that in the late 50s, early 60s. They were still learning that nuclear needs a little bit of caution, appropriate caution. Okay. So, how do you do the impossible? Well, one method would be to assemble a team of experts, define the roles and responsibilities, divide up who manages, who steers, who actually bends the tin, and so on. How many people here have worked at a company that's how things were done? From that silence, I take it all the listeners are unemployed and never have been employed. Is that correct? Has anybody been employed?
Yes.
Yeah.
Okay. Does this sound like normal corporate business design for tackling a project?
Absolutely.
Yep.
Mm-hmm. Well, that would have failed because the NOVA project wouldn't have found out that it couldn't land on the moon until the first time they tried it. And then depending on, they might or might not have survived, but they wouldn't have landed. And might have had other problems even before then. That works if you know exactly what you're doing. It doesn't work when you've got unknowns. And any unknown that could throw a severe monkey wrench in tends to be fatal to such an approach. Okay? Systems engineering is where you design your approach based on mathematical and physical and statistical principles. Okay, what in systems engineering was not invented by NASA. It actually goes back thousands of years, even back to the Bible. The math and statistics started to be applied to it in the 19th century and early 20th century. Anybody here hear of the know who the Gilbreths are? Any heard of a book called Cheaper by the Dozen? Okay,
Time and motion studies.
that's exactly right. Time and motion study was the mathematization of the systems engineering. That's where they made the measurements on which to base the design of engineering work. Before then, there were guesses, but the Gilbreths literally wrote the book on how to do the practical measurement. And several of the things they came up with are in use today. How many people, for instance, have seen in either in a real operating room or on TV where the surgeon says scalpel and the nurse picks it off the tray and bangs it into his hand? That was one of the Gilbreth's idea that's still in use. Now, that had actually most companies in the 60s practice systems engineering, but NASA became the epitome of it. They took it to extremes, and as part of that, came up with some very good, useful tools. All right, the solution to doing something quickly and survivably is what's called a tiger team, is what at the time of NASA was called a tiger team. And basically, you'd have many different teams. How many, is there anybody here who saw the Apollo 13 movie with Tom Hanks?
Yes.
Okay, one person saw it. All right. In that movie, do you remember the scene where the team lead comes in and says, they've handed us this one from above. We need to make this canister, square, fit into the hole designed for this canister, round, and do it with this stuff spread out on the table. Anybody remember that scene?
Oh, yeah.
CO2 scrubbers.
That's right, CO2 scrubbers. Okay, what wasn't that clear from the movie was the fact that they didn't just hand that to one team. That was a critical problem. So it got handed to approximately 1,000 teams, each one given different sets of stuff to try and make it from and different approaches. For instance, they weren't using the service module engine, but the service module engine had liquid oxygen as one of its fuel components. How many people know that one of the solutions they looked at, one of the Tiger teams came up with, was to do a spacewalk and bleed the oxygen out of basically tear apart the back end of the service module, get at those oxygen tanks, and use that to bleed recover the service module. In other words, every so often just flush all the gas out of the service module and replace it with oxygen from those tanks. That was one of actually the ones that might have worked, but and if they'd that in fact would have been one of the comparatively low risk ones, comparatively. All right. Um, they had quite a few of them. Now, by having the tiger teams and giving them different ones, though, you get the first answer that works best is the one you take. And it was normal at that time for businesses to, whenever they had a project, they would hand it to multiple teams, not one. In fact, in the 1960s, general wisdom was that putting one team on a project was a good way to commit commercial suicide. So it was normal to have about 2 or 3 teams tackling every project. Now, that meant that 2 out of 3 times you were probably going to be on the team that didn't succeed. But that's okay. That just meant that when some other team succeeded, you got shifted to a new project and a different team. They didn't lay the people off. They called them staff engineers. And it was obvious. Usually there was bonuses for those who succeeded, but they didn't lay anybody off for the project not working. As I said, that would have been considered commercial suicide. How many people today have seen that really is commercial suicide when a company tries to hit the ground running with nobody, with a new problem, and then finds out that some competitor beats them even after they've invested in, put a lot of investment into trying to make whatever they came up with first work. Anybody? Anybody not seen that? Oh well. So, now, most companies normally didn't take it to NASA's extreme, but NASA was under, especially in the case of Apollo 13, when you hear the phrase from Gene Kratz, for instance, call everybody in, get everybody who worked on anything in here, and get them working these problems. Working these problems meant exactly like the one with the CO2 scrubber problem. There are lots of others, though. They had in Apollo 13, they showed the battery problem, that they needed a way to restart the command module. In the movie, they made it look like Ken Mattingly was the only person working on that problem. But again, that was a critical one, so they had at least hundreds of teams trying to tackle that from various solutions. And if I remember, as I understood it, they actually didn't get. They actually, that was one where they actually combined 2 different teams partly in, namely the idea of stealing inefficiently electricity from the LEM batteries to top off the command module batteries was one that came out of a separate team, not part of one of the teams trying to develop the minimum current startup procedure. Now, at that time around the country, different companies were at different extremes on that. RCA was one, the poster child for all the teams talking to each other regularly. So if you were on a team dealing with a problem like how to best manage CDs, and CDs, by the way, came out of RCA in the 1960s, 1970s. If you look on Wikipedia, it says they were invented in '86, but that was when Philips or Sony or whatever it is bought the rights from RCA. Prior to then, they were distributed in a red cover book, red being RCA's colors, hence the reason the compact disc digital audio format is still often known as the red book format. But and HP was at the opposite. Hewlett Packard was at the opposite. Their policy was that the teams working on the same project never talked. And there's benefits on both sides. So most companies were somewhere in between. Okay. Now, this particular one, the original starting, was the Tiger teams in specifically. They got the name because their goal was to basically find anything that could go wrong. Try to break the system. Try to make sure things went wrong. Because if at the point in time when they couldn't break it anymore, that was it was figured it would work, and that was one of the fastest ways to find out what could go wrong and what would survive. Okay. Now, part of the math that came out of NASA, out of the Apollo program specifically, was a good rule of thumb for how you allocate your resources. Now, by the way, this model actually goes back to the 19th century French mathematicians, but the proof of certain proofs regarding it didn't exist until the Apollo program, and as a consequence, it wasn't nearly so well used. It turns out you get your maximum throughput when you per resources, when you allocate the resources by this formula shown here. The likelihood of success times the benefit divided by the square root of risk times estimate error. Now what that means is you don't just try what you expect to work. You try things that you expect to work, things that you don't expect to work, but if they did work, they'd be better. And you also try things that haven't been proven impossible, but nobody in their right mind would think they were going to work. And in the case of Apollo, we got some of our best results out of some of the more outlandish things. And I'm using that isn't an intended double entendre. So, for instance, how many people know how they got the rock samples off the surface of the moon? In most of the science fiction movies, you see them using an elevator or a winch system or something else to, like a dumbwaiter, to bring things up and down from the ship. But what they actually ended up using was a clothesline. Lightweight, easy to set up, very tolerant. And so they just they attached their sample bags to the clothesline, one person on the surface and one person at the door of the limb. Okay. Some things that everybody thought would work failed. The NOVA approach. Okay. Some things were in between. Velcro and GPS were ones that made sense, but they hadn't been tried before. And I'll get into Velcro if somebody asks a little later. The Velcro, as we think of it today, is significantly different from the Swiss patent that you'll find that will be referred to by the French and the Japanese companies that now sell Velcro. They claim that Velcro came from the Swiss in the 60s and not from in the early 60s or late 50s, I forget, and not from NASA. But it's, well, you can check the patent yourself and see how close you think it is. The original Well, then we'll get into that one later if we get to it. Medium risk. Okay, and then the high risk attacks, some of them failed. Example, unfortunately, was the Apollo 1 disaster that resulted from the pure O2. Now, they were gambling when they selected the O2, which made the craft lighter and thinner, that everybody would abide by the requirements for flame retardants and non-flammability. And unfortunately, it took only a few to turn the pure O2 environment into a fatal disaster. But some of the other high-risk attacks worked very well. Man-in-the-loop, cruise control, photolithography multiplexer. That's the basis of microelectronics. You had told people in the 1960s that we would have electronics based on sand etched like tombstones, with the technology used to etch tombstones. You'd have been very hard pressed to find anybody that considered you other than completely insane. But it was one of the outlandish ideas, so ridiculous ideas, that was tried and worked well and started the microelectronics industry. Okay, so that's systems engineering. We're down to 17 minutes. Let me go to the end, and then we might look back at one here. Let's see, where was the end? Somewhere here I had. Oops. Well, find it later. All right, so we've seen three: GPS, cruise control, and system engineering. The systems engineering was given a major boost by the millions of dollars that was invested in the experiments to mathematize the general approach of try everything, don't keep that which is good. That's from the Bible. Don't put all your eggs in one basket. Don't count your chickens before they're hatched. These witticisms had, of course, been around for centuries, but turning that into a mathematical formula for how to optimize that came out of NASA investments for Apollo. Okay. The cruise control, seemingly such a simple idea. We might or might not still have that today, but again, it came out of trying to solve a problem that hadn't seen any attention. There was no, prior to Apollo, there was no real reason for anybody to be looking at it. It wasn't, again, to use a double entendre, on anybody's radar. People had been lashing helms and adjusting jibs and trim for centuries, and that was generally considered good enough. There was no reason for devising a better method. Of course, from that better method, we now have lighter weight cars that are more fuel efficient. We have aircraft that with guided pre-programmed control are more survivable, lighter weight. We have appliances that we are used to tweaking and programming to a degree that not even the Jetsons cartoons predicted. And by the way, the Jetsons were, in case you're not aware, Hanna-Barbera actually set the Jetsons in the year 1999. And in the 1960s, when that was made, that view of how the next generation would live was not unreasonable. We didn't see most of the things from the Jetsons, but most of the things we have seen weren't dreamed up in the Jetsons, largely because they didn't predict an Apollo program or its equivalent. Okay. Any questions? Any details, suggestions? Okay, so next time somebody tells you the moon landing was a hoax, point them at GPS. Next time you're looking for how to accomplish something quickly, look up how to work Tiger teams. Did I lose my audience? Is anybody still there?
Still here.
Okay.
We're here.
All right. Well, that comes close to 8, but if you want, you can go over lasers and Velcro or microelectronics. It's up to you.
Go ahead with the lasers, Robert.
All right. Okay. The Apollo program was originally supposed to start regular travel between the Earth and the Moon. In the 1960s, it was figured that we would have people by 2000 not only living in quantity on the Moon, but actually by that time homesteading the asteroids or maybe some of the other planets. And the Moon was the logical fuel stop, much easier to land on and take off from than Earth, or so they thought. The problem, though, was to reduce the cost of future landings. Given how difficult it was to land the first time, they wanted to make it cheaper in future flights. Imagine landing on a beach where you don't know, there's no charts regarding what's there, there's no piers, there's no wharfs, and so in order to make future use of that beach a lot less expensive, after you make the first landing, you try and put in the wharves and clear the debris from the water around the beach, cut channels, put markers to keep people clear of problem areas. So they, in the first few engineering flights, Apollo 10, Apollo 11, 12, 13, 14 were supposed to be engineering flights, followed by science flights, 15 through about 19. And the original sequence actually called for going up through Apollo 26. Every one of the then Apollo astronauts was supposed to go to the moon twice. And that's what they had the rotation originally set up for. Now, as part of that, the second landing, which might have been the first, Apollo 11 did not have, when they launched for Apollo 11, they weren't certain of landing on the moon. They were going to make the attempt, but if they found out the Apollo 10 calibration wasn't adequate, or there was some other unexpected problem, which it almost turns out there was, Apollo 12 would have been the next attempt and the more likely first landing, successful landing. And Apollo 11, in fact, they were originally, as said, supposed to do planetfall manually with the cruise controls. Then switch to the DIDO, the Governor Automatic System, but for political reasons they were going to shut that off just basically at a low enough altitude. They could say it was a manned landing. But it turns out they actually needed that because when they hit the high gate and tilted over to look and got the first look, Neil Armstrong described it as a boulder-strewn football field. Where they were heading, their survival would have been very unlikely. In fact, if you look at the pictures they took, you can see in several of the views the boulders in the background. But Neil Armstrong took over manual control and translated significant distance to find a area free enough of visible boulders to make the successful landing. So, how do you mark where are the safe landing spots that you can see from a far distance? Anybody got any ideas how that would be done? How's that done on Earth? Any ideas? Okay, well, they had an opportunity to leave something on the moon, and the way it's done on Earth is you use signs. You use signs, you use stripings. How do you know where your safe lane is on the road? They stripe it. They put paint down the center, and you stay on your side, and the other traffic stays on the other side. How many people here have driven on busy roads with no striping? It's a lot more difficult.
Yes, it is.
Well, there were no stripes on the moon. So, they added them, but they couldn't add full stripes. VASI, Vertical Approach Slope Indicator, is used in aviation. It's basically a lighthouse. Does everybody know what a lighthouse is? Is there anybody who doesn't know what a lighthouse is? Okay. VASI was two lights, a small number of lights, which have some shutters in between them, so that if you're coming in too high for the airport, you see two white lights. They're unshuttered to you. If you come in too low, you see two red lights. And if you're coming in just right, you see a red light over a white light, and the other lights are shuttered away from you. So they wanted to do a similar thing. Now, VASI requires a power source, and so do lighthouses. So they wanted something that didn't require a power source that was going to run out. Well, how do you power it if you don't have a power source? Anybody know what retroreflectors are? Anybody ever wear retroreflectors? Anybody ever go jogging with a reflective vest? Okay, well, do me a favor. Don't go jogging in my neighborhood if you don't want to wear a reflective vest. But the retroreflectors, they work by reflecting light back from whatever direction it comes from, which means that if you put those somewhere, you can power it with the light from where you're also observing it. And so somebody came up, one of those tiger teams. As I said, they would have had lots and lots of different teams trying this with lots and lots of different approaches, ideas, and limitations. Now, Foucault measured unknown light speed in the 19th century using a retroreflector put on a mountain a few miles away. He knew the distance. He knew by rotating a set of mirrors, he could measure the timing, and from that could calculate light speed. Works the other way too. You can calculate your distance by knowing the speed of light and measuring the time that it takes for the reflection from the retroreflector to come back at you. That's sort of what radar does, where you treat the your target as a retroreflector, but unfortunately you got to give it a lot of power because most of the reflection isn't going to come back at you. But if you use a retroreflector, it can be small, it doesn't have to be moon-sized, and it'll give you back enough to calculate your distance or identify where it is and thus where you can safely land. Okay, so they put retroreflectors on the moon in the Apollo missions, and some of them are still working today, which again is evidence that we had humans on the moon, because some of the I think 3 of the laser reflectors they left there are still working. Now, in 1969, the best collimated light source was only collimated to about 1 millimeter over 300 meters, because that was about the best you could do on Earth at sea level pressure. If by the time you start going beyond that, you get the blurring of the Purple Mountain's majesty. In other words, the air starts to spread the beam, no matter how well collimated it is. If you know antenna theory, that collimation corresponds to about 97 dB. Okay, that's the antenna gain. But if you scale that to lunar distance, that collimation still only gets you down to 1 kilometer, which means if you haven't got your radar reflector is only a square meter, you're only going to get back about minus 120 dBs on that. You're not going to get all that much back, or you're going to need a very, very strong laser, which of course is what they used in the 1960s. But also meant, though, that they couldn't tell where anything was on the moon or measure things very precisely. Also because of atmosphere, the fact that the spreading medium, the atmosphere, is close to the sender and far from the reflector, means it scatters the light a lot further, about 40 kilometers. So, but though they didn't actually use it for lunar landings, we never did get, unfortunately they stopped it before they revisited or even created a lunar base. Subsequent to that, since the 1980s, they've used those laser pointers to collimate lasers and things inexpensively. It's very hard to set up a laser testing lab on Earth to see how to get something more calibrated than that 3 football field distance. But by going to the moon, they could continuously check the strength of the reflection as they tweaked the various designs for the lasers. So we ended up getting the inexpensive high-gain lasers that we have today as a side benefit of the Apollo program specifically, that put those lasers those laser reflectors out there. Also, since the 1970s, the track of the moon has been used as a test of gravitational theories regarding both the sun and cosmology. So anything made with a laser today is a lot cheaper and more precise because of the relatively inexpensive addition of putting those laser reflectors on the moon. You can see a pic. I think I got a picture of one of them here. Let's see, Apollo experiment. See if that's it. Nope. Somewhere on here. Let's see. Oh, maybe it is here. Okay, there he's carrying the kit. See if there's one of the lasers out there. Ah, there we go. There is one of the laser reflectors. Very lightweight, so it didn't cost as much. In fact, it should be lighter than one of their boots. So it costs less to transport that to the moon than one of their boots. And the profits from that the laser industry made from these would alone be enough to pay for more than the entire Apollo program. It was about 17 billion, and the laser industry in 1 year makes more than that. Okay. Well, we got 2 more if you're still interested. There's 3 more. Microelectronics, Velcro, and I think that's it. Yeah. Anybody interested in microelectronics, or anybody got any questions or other examples with regards to laser? Okay. So, do you want to draw this to a close, or anybody interested in microelectronics or Velcro?
I'm interested in well, I'm interested in both, actually. So if you want to drop off, we're not gonna, we're not your mother. Go ahead. Go ahead and drop off. But okay. Yeah, keep talking about it. I'll listen.
All right. Well, let's see. Let's do Velcro next, because microelectronics is all right. Where's Velcro here? Okay. The problem was a removable attachment. You're in weightlessness. You have to do things. You have to manipulate things. How do you manipulate things, keep track of tools and parts when you're doing anything in a nearly weightless environment? Anybody try to assemble something underwater in a pool where the current will take things away from you, where some pieces will float, others will sink away from you? That's the problem. Anybody here see the repairs of the Hubble Space Telescope by Atlantis? Anybody remember those in the 1990s and aughts?
Vividly.
Good. Okay. Now, when you something you can probably confirm, did you ever see them? If you were removing a bolt from something here on Earth, you would use a wrench and turn it, right? Did you ever see them use a wrench to do any of the unscrewing they did?
Nope.
Okay. Did you also notice what was attached to the rotary tool they did use, the basic grabbing screwdriver that they used? What was attached?
A bag?
Right, they had bags attached, exactly. They put bags over stuff. In fact, that's where they put all the nuts and bolts they removed, was into bags. How about lanyard? Do you remember the lanyards that were reeling themselves in and out all over the place?
Oh, yeah.
The reason they had those was because if you let go of a bolt, it's not like in the movies. It doesn't just stay there. It's got sunlight shining on it. It's got residual atmosphere going by. It's feeling a slightly different gravity due to tidal effect. In the case of the space shuttle had its own gravity field that caused things basically to fall to the floor of the cargo bay slowly, and slowly enough that, in fact, just with a light brush of a finger, you could push a bolt out of the cargo bay, where you'd A, never see it, and B, have a hard time recovering it. Unfortunately, if you have if it leaves the cargo bay, it's in orbit around the Earth just like the shuttle is, and it's in an orbit, in fact, that is almost on the same great circle, which means half an orbit later, that bolt's coming back. Depending on what tidal and sunlight forces it feels in between, it could come back at machine gun speed. So it was very important not to drop things. Not something that usually made it into the movies, but it was very important in real space efforts. Space debris is a real problem.
Also,
It's a manageable
hold
problem.
something at exactly the right point where it will theoretically stay in place is very difficult too, akin to balancing a playing card on edge.
And it's even worse because there's a wind going by. Consider, has anybody here seen a radiometer? Usually one of the common forms was a toy that had an evacuated glass bowl, and inside it, hanging on a wire pivot, was a set of 4 flags painted black on one side and white on the other. And when exposed to light, the flags would turn. Okay. That happens because of, if it's an evacuated sphere, it happens because photons have momentum. And when they are reflected by a white surface, that momentum is reversed. Well, for every reaction, such as reversing the photon momentum, there is an equal and opposite reaction. That flag gets pushed. And so in an evacuated sphere, the white flag faces would be pushed away more than the black ones, which absorb the photons, would. And so the thing starts spinning away from the white. Well, it's a pretty hard vacuum near the Hubble Space Telescope. Hard enough that a bolt, if it's not identical coloration, is going to start spinning like one of those radiometer toys. And that spin, if it has any non-symmetry to it, is going to mean that bolt is going to get pushed away. Now the force is light, the acceleration is small, but there's nothing to stop it. Further, we talked before about the Earth having a non-uniform gravity field, that it varies quite a bit. Well, that means as you're orbiting the Earth, it's like dipping in and out of valleys. Imagine rolling a marble